So a reminder, we started covering the central limit theorem this week for hypothesis tests and confidence intervals. And the central limit theorem tells us a couple of things. Sampling distributions are relatively normal in shape. And so that means they have this symmetric bell shape. And there's actually a formula for the normal distribution that Statistic takes advantage of in one of its apps that we're going to look at today. So that's one thing about the central limit theorem. The second thing the central limit theorem says is that the mean of the population, mu, is going to be about the same as the mean of the sampling distribution. So this mu right here, again, is population mean. And then I mentioned this mu with a little sub x bar there. That's from the sampling distribution. Now, we generally don't have the ability to run thousands and thousands of samples of size 50, for example. So for both of those, we rely on a single sample. And so we tend to approximate those with the actual sample mean. So central limit theorem says for a big enough n equals 30, 50, 100, the bigger it is, the better. Usually the minimum cutoff is 30, but sometimes we can get by with less depending on the situation. And so this is the second thing from the central limit theorem. And the third thing we're going to use today from the central limit theorem is related to the standard deviation of the sampling distribution, and that's called the standard error. So that tells us the spread we can expect for samples. So sample statistic spread. And we need that spread to calculate p-values and to find margin of errors on confidence intervals. So let's play with the normal distribution calculator in Statistic. So I have some questions to help us do that. So here's a hypothesis test. So what I want to do here is I want to find the value of the standardized Z statistic. I'll remind you of what that is for a given hypothesis, sample statistics, and standard error. So I'm given my hypothesis here. So my null hypothesis is that I have a mu that's thought to be 85. And my alternative hypothesis is that the mu is believed to be greater than 85. And remember, for the null and the alternative hypothesis, the null has an equals, the alternative never has an equals in it. That's how we choose which is which. Then I've got some sample data. I have a sample of size 25. My sample had a mean of 85.036. Now the question is it's higher, right? But is it a lot higher? That's what we got to look at next. And that depends on things about the population, in particular, the spread. Now, S, that's the sample. This SE over here, that's the sampling distribution. And that right there is what I need to make some calculations. So there's 3 different ways we use z-scores in this kind of thing. One way is this idea of a standardized test statistic. Played with this a little last class in previous videos. Standardized test statistic. And it's going to look something like this. It's going to be usually a sample information, maybe the sample mean or the sample proportion, minus the population information, which is generally from the null hypothesis, divided by the standard error. So in this situation right here, for my Z, I would take my X bar subtract the mu from the null hypothesis, and divide by the standard error. And the standard error either has to be given, found in a sampling distribution randomization, or calculated in another way we'll talk about next week. So for now, I'm just going to give you the standard errors. So pretty much any problem I ask like this, where I want you to find, say, a z or a p or a margin of error, I'm going to say, hey, this is the standard error. So pay attention to that. All right, so for this one, I get 85.036 minus 85 divided by the spread of the sampling distribution, 0.72, and we whip that out on a calculator. And here I just need a regular calculator. So I'm just going to bring that off the side so I can see my numbers again. Double check me on this in case I mistype anything. 85.036 minus 85 divided by, oops, not subtract, divide by 0.72. All right, so if I typed it right, let's bring this over here and take a look. So I've got my 85.036 minus 85 divided by 0.72. I just type that in Google search, Google whips out the calculator, and I get 0.05 as my z-score. .05. All right, reminder, what is a z-score? A z-score counts standard deviations. So if I think about a normal distribution, which is that symmetric bell shape, and it's a good idea to draw pictures with any problems like this from now on. If you haven't been doing that in your notes, I can encourage you to do so. So here I'm going to put mu in the middle. And mu in the middle is a z-score of 0. We haven't left the center. Standard deviation counts how far away from the center are you. And with z-scores, we expect within 1, 2, 3 standard deviations on each side. So 1, 2, that would be -3 on the other side. So here's z equals -3, here's z equals 3. We expect about 99.7% of the data to be in that range right there. Within 2 standard deviations, we expect about 95% of the data to fall in there. And that data could be the population, the data could be the sampling distribution, if they have a normal distribution. So for us, the only thing for sure that has a normal distribution is the sampling distribution. And that's what this spread is from here. Sampling has a normal distribution. Now we get a z-score of 0.05 right there. Well, if this is 1 and that's 0, 0.05 is like right here. That's my z-score is right here. So is 85.3036 far from 85? The answer is no, it's snuggled up right up against it right there. Okay. If I were to calculate a p-value for that, this question didn't ask that, but the p-value would be what's the chance of being bigger than that number right there? My p-value is going to be pretty darn close to 50%. Right, which means, this data seems to support the null hypothesis, so I'm just going to fail to reject the null hypothesis. All right, so the point here was calculating a z-score. One way to calculate a z-score is given a null hypothesis and sample statistics and the standard error. So we need information from the population, information from the sample, and we need a little information about the sampling distribution. 3 separate things have to come together. All right, let's try another one.